Happy Monday morning. We're finishing up with polynomial rational functions today. We look at variation. Broadly, there's two types of variation that we look at. First is direct variation. XY related in the form y equals kx to the n. This relationship is known as direct variation. We say that y varies directly with the nth power of x. We would also say that y is proportional to x, or x to the n. K is called the constant of proportionality. It's a very simple relation, but it also happens to occur quite a bit. And the second type of variation inverse variation. Right, so we have a relation y equals k over x to the n. We say that y varies inversely with the nth power of x. Right, and we'd also write it as a proportion. Y is proportional to 1 over x to the n, or y is inversely proportional to x to the n. And again, inverse relations also happen to occur quite often. There are two very common in particular in physics that we will look at. Well, we look at one in this class, and I'll introduce the other, because I only have an example for one of them.
Is it only in this class of physics, not calculus?
Well, physics is applied calc. So you obviously look at them in more depth in calculus as well. Like, we're not going to get super in depth in them here. I'll just show it to you. S varies directly as the square of x. And we know that s equals 5 when x equals 4. Find s when x is equal to 20. And again, we could also say that s is proportional to the square of x. Right, s is proportional to x squared, which means that s is some constant of proportionality k times x squared. And this is technically an if and only if. They mean the exact same thing. So if s is a constant times x squared, you can say that it is proportional to x squared. We have to find that constant of proportionality. Which generally requires you to do experimentation. But here, they gave us the results of some experiment. They said that when x was 4, s measured to be 5. Winds up with k being 5/16, right? Then that would be the model for this problem. S is 5/16 of x squared. Now, what is s when x is 20? There's no need to actually evaluate 20 squared. Twenty is 5 times 4, isn't it? Twenty squared would be 5 squared times 4 squared. But 4 squared is what? And there's a 16 in the denominator. This is 5 cubed. And what's 5 cubed?
125.
So when x is 20, s is 125. Y varies directly to the cube root of x, and y is 12 when x is 64. We have to find that constant of proportionality. What is the cube root of 64? It's 4. Which makes k what? If 12 is 4 times k, what is k? There's the model. Y is 3 times the cube root of x. Now, what is y when x is an eighth? Cube root of an eighth. What is it?
Half.
So y is 3 halves. I inversely proportional to the square of t. Right, that would mean that I is some constant over t squared. I is 100 when t is 15. What's 15 squared? So what's k?
This is 100 times 225.
Which is what?
22,500.
There's our model. Now when t is 12, what is I? And what did we say 22,500 was? It was 100 times 225, right? But 10 is 5 times 2, so we can write it this way. And all this without a calculator. 3 squared over 3 squared is gone. Oh, but 4 squared, isn't that 2 squared? Oops. Left with 5 to the 4th over 2 squared. What's 5 to the 4th?
25.
I is 625 over 4. And we didn't need a calculator. U varies inversely as the cube root of x. We have to find that constant. What is the cube root of -8?
-2.
What's k?
-112.
There's the model. Now, when x is 1,000, what is u? Cube root of 1,000.
10.
Oops, not 2. Negative 56 over 5. Z varies jointly as x and y. So joint variation is just multiple variables. So it could be direct variation with more than one variable, could be inverse variation with more than one variable, or it could be a combination. Maybe it varies directly with one variable and inversely with another. In this case, z is proportional to x times y, which means z would be k times x times y. If z is 3 when x is 4 and y is 6, then 3 would equal 24 times k, which makes k 1/8. So we can say there's our model. When x is 20 and y is 9, what is z? Twenty times 9. So we look at the last two digits of 180, it's 80. That's divisible by 4, which means 180 is divisible by 4. It's 45, which is not divisible by 2, so there you go, 45 halves. P varies jointly as the square of x and fourth root of y. We've got k. P is 24 when X is 12. Y is 81. Twelve squared. What was it? 4th root of 81. What is it? The 24 over 3 is 8. 144. So 8 over 144. We could also divide by 12 first. That would give 12 is equal to 36K. Or 2 is equal to 36K, sorry. And then 2 over 36 would be 118. So K is an 18th. Oh boy. What's 1200 squared? You don't need a calculator. What's 12 squared?
144.
What's 100 squared? It's 10,000. It's 10 to the 4th power. Now 144 times 10,000. That's 144 with 4 zeros after it.
1.4 million. 44 million.
Yeah, 1.44 million. But like I said, just 144 and then 4 zeros. That's 1200 squared. See, things that are divisible by 10 are very easy to square. What is the 4th root of 1/16?
1/10.
All right, so again, go simple. 144 over 36. is 4. So 1.44 million divided by 36 would be 40,000. Very easy to work with powers of 10.
How did you get K equals 1 with?
I divided 144 times 3 on both sides. So 24 over 144 times 3. Easiest way to do that is 144 is 12 squared, right? What's 24 over 12?
2.
You're left with 12 times 3 on the other side, so 2 is equal to 36k divided by 36. What's 2 over 36?
1/18.
There's your 1/18. And again, all without the need of a calculator. So now we're going to look at some applications. One of the more well-known applications of direct variation. This is also a very common example when you first start looking at work in physics. You use springs. This is the end of week 6. Wouldn't intro mechanics have gotten to work yet? Should have. Oh wait, you probably haven't had physics yet. High school physics.
Yeah, it's a good in high school.
And I know you covered this.
Work.
What law governs springs? Because high school physics does do work.
No, I never did.
High school physics is intro mechanics without calculus. It's algebra-based mechanics.
Yeah.
Which is kind of a joke because you need calculus for mechanics, but it's intro. Hooke's law.
Talking about springs, like what kind of like potential
Hooke's-
energy?
Hooke's law governs springs. Hooke's law essentially says that when you stretch or compress a spring beyond its natural length, the spring exerts a restoring force that is proportional to the amount that you stretched or compressed it. Right, said another way, force needed to stretch a spring x units beyond its natural length is directly proportional to x. I always hated drawing the proportional symbol. Which means that F is K times X. K is called the spring constant. Every spring has a unique spring constant. You can have a manufacturer make 100 springs, and I guarantee that each spring has a unique
a different spring constant. How do we find it? We have to perform an experiment. Well, they did. They found that it took 6 pounds uh-oh, I'm missing information here.
Yeah, where is it?
And that is in proper English, it's 1/2 inch. There we go. Took 6 pounds to stretch it 1/2 inch from its natural length. Find the force necessary to stretch the spring by 2.25 inches. So it took 6 pounds to stretch it 1/2 inch. So what is K?
Well,
12 what?
pounds per inch. No.
You're right.
Yeah.
However, it's not set as pounds per inch because this is not a rate of change. And that's a hyphen, not a minus. So we'd say K is 12 pound inverse inch. Right, but you're not wrong if you do pound over inch. We just don't say it as per because it's not really a rate of change. So how much force does it take to stretch it 2.25 inches beyond natural length?
So 27 points. Inch in.
Oh, you know what? Yeah.
I think it's 27.
Right, it's 24 plus 3. Yeah.
Sure, yeah.
So it's 27. What did you say it was? 27 what?
I know it's pounds. I forgot how you read that. Pounds
Pound.
per inverse inch.
Forces pounds.
Oh, it's just force.
Because it'd be pound inverse inch times inch. right? Because X is in inches.
Yeah.
So it'd just be pounds you'd be left with.
That's
Takes 27 pounds of force. You can tell that the author of this source is not a science person because they use the wrong units of measurement. So this is just actually a bit of interesting tidbit. So force being measured in pounds means that your weight is a force. What is the standard unit, the SI unit for force?
newtons.
The Newton. But what do they measure your weight as?
Kilograms.
Kilogram is a mass, not a weight. Which is a problem. Shouldn't be kilos. Should be newtons. Ohm's law. If you have to take E&M, you're going to hate Ohm's law. Ohm's law states the current in a directed current circuit varies inversely as the resistance. If a resistance of 12 ohms produces a current of 3.5 amps, find the current when the resistance is 2.4 ohms. Right, so current inversely proportional to resistance K over R. We know that 3.5 amps would be K over 12 ohms. You recognize that symbol, by the way? It's a Greek letter.
It's omega, right?
Be more specific. It's not omega. It's capital Omega. That's omega. Capital Omega. So what's K? Twelve times 3.
36.
Half of 12.
6.
Atom.
46.
42. Ohm amps. And again, that's not a minus, that's a hyphen. What is amp short for? See if you know it. Amp isn't the unit of measure, it's shorthand for the unit of measure.
I switched it up in here.
It's the ampere. So it's what? I 42 over R. $42 over 2.4. So that's what 2.4 is 2 1/5. No,
2 2/5.
2 2/5. So it'd be 12 over 5. So it'd be 42 times 5/12. 7/2 is 42 over 12. So 35 halves. And I'll write it back as a decimal, so that's 17.5. Uh-oh. There we go. 17.5 what?
Amps.
17.5 amps. Circuits are horrible. Pressure of wind on a wall varies jointly as the area of the wall and the square of the velocity of the wind. Oh. So that's not entirely correct. It's misworded. Area. How many dimensions
2.
is a wall 2-dimensional?
No.
No, it's 3-dimensional. It also has thickness. So that shouldn't be area, it should be what?
Volume. Yeah.
It's not called area for 3-dimensional.
Length, width, height.
Well, that's volume if it's
I
rectangular.
thought it was volume.
But it's not volume because it doesn't. The pressure doesn't depend on the depth or the thickness of the wall.
No.
Surface area should be the. This is the proper term there. So that should say it varies jointly as the surface area of the wall, right, or area of the surface. And the square velocity of the wind, that's fine. So P is 100 pounds. Here we go again with the empirical measures. When surface area is 80 square feet, and speed of the wind is 40 miles per hour. Oh boy. 40 squared is 1600 times 80. 8 times 16. 8 times 6 is 48. 8 times 10 is 80. So 80 and 48, 128. And it was 100 times 10, so 3 zeros. Feet squared times miles per hour squared. So 100 divided by 128,000. One over 1280. And units. Would be the pound inverse foot squared inverse mile per hour squared. Which I'm pretty sure can be simplified. I don't remember what pounds are. I don't remember if that's foot per mile per second. Might be. Oh, be foot per mile per second squared, I think is what it is. But since I'm not 100% sure, I'm just going to leave it like that. So there's wind pressure on the wall. I think that's actually true in general. It doesn't just have to be a wall. Right, the pressure that the wind exerts would just be proportional to the area of the surface times the square of the speed of the wind. this might require a calculator. We'll see. 12 times. So what's 50 squared? This would be,
2500.
yeah, it's 2,500. Divided by 128. So that was the easy part of just getting rid of the tens. But 12 over 128 can simplify. What does that simplify to? 28 is divisible by 4. So it's going to be 3 times 2,500 divided by something. 128 over 4. That's what?
3 over 32. No,
Yeah.
no, that's not.
What's half of 128?
64.
And then half of that is 32. $2,500 is also divisible by 4. And so is 32. So that would be 3 times 2,500 over 4.
625.
Yeah, that sounds right. Over 8. Yeah, and then what's 3 times 625? 3 times 600 is 1,800. What's 3 times 25? 75? 1875. 1875 over 8. Pounds.
Just pounds it.
Just pounds. Because pressure is measured in pounds.
Oh,
Oh, look, I didn't need a calculator after all. If I wanted to write that as a decimal, I wouldn't need a calculator because I don't know what that is. I'm just going to leave it like that. Ah, yes, this one. Okay. Rate of an object on or above the surface of the Earth varies inversely as the square of the distance of the object from the center of the Earth. This is a generalization of Newton's law of gravity. Says that the force of gravity is inversely proportional to the square of the distance from the object. That means F is k over r squared, but we found out what k is. Capital G is the universal gravitational constant. Capital M is the mass of the larger object, and little m is the mass of the smaller object. Newton's law of gravity says that every object of mass exerts a gravitational force on every other object of mass, specifically a gravitational attraction. And I think G, if I remember correctly, is 8.67 times 10 to the minus 11.
The gravitational constant? I think it's 6.7.
Is it 6 point?
It was a long time ago. Yeah. 10 to the negative 11? Yeah.
It's definitely 10 to the minus 11.
Might not be exactly 6 points.
Where's my search feature? Why are you not letting me search? There you are. $6.674 times 10 to the minus 11. By the way, that means gravity is a very weak force. And it's very hard to think about. But it's very easy to overcome gravity. You do it every single day. When you lift up your book, you just overcame gravity. When you jump, you just overcame gravity for a little bit. We've already overcome gravity by leaving Earth's surface and going to the moon. So gravity is very easy to overcome, except for a black hole. Yeah, there's no overcoming that gravity. You're just dead. This is known as an inverse square law. Force is inversely proportional to the square of distance. It's not the only inverse square law in physics. There's also another very common one. Electric force is an inverse square law. That is, what do they use? I think it is K. Pretty sure it is K. K times charge 1 times charge 2 over the square of the distance between them. And that's a repulsive force.
That's what charge is.
Right, so every particle has charge, either positive or negative. If the charges are the same, that's a repulsive force. If they're different, then it's an attractive force. Whereas gravity is always an attractive force. Gravity never repulses. It always attracts. Electric force and magnetic force are either attractive or repulsive depending on the situation. K is a constant. The hell is it? It's been so long. Oh, I'm sorry. They use K sub E. Is it that? Yep, okay. Yeah, it's a very large quantity. So if we're dealing with air or a vacuum, that K is 9 times 10 to the 9. More specifically, it's 1 all over 4 pi epsilon naught times epsilon r. Epsilon naught is a fixed constant. Epsilon r is permeativity. So permeativity of the medium, which again, you don't really need to know. You'll study that if you take intro E&M. Even then, I don't even really think you study it that much. That's more advanced. So again, very large. Those are probably the two most common. Oh, and by the way, since electricity and magnetism basically the same, there's also a magnetic force that matches that. Except instead of charge, you use magnetism. Otherwise, it looks identical. Right, so we're told an astronaut weighs 120 pounds at the surface. How much to the nearest pound would he weigh in a satellite that's 400 miles above the surface? And we're using 4,000 miles as the radius of the Earth. And we're also ignoring altitude. Because obviously this would also depend on his altitude. 4,000 miles is the radius at sea level. Which we didn't know that. We're gonna assume that the surface of the Earth is completely flat. It doesn't have any altitude to it. Uh, 4,000 miles squared. $4,000 squared. $16 with 6 zeros. So 16 million. K would equal 120 times 16 million. What's 12 times 16? 12 times 10 is 120. 12 times 6 is 72. So it'll be 192. With 7 zeros. I'm going to make life easier. Right. No, it's 8, right? Oh, wait. No, that's 7. That was right. 1.92 times 10 to the 9th. So how much would he weigh in a satellite that's 400 miles above the surface? Why am I did F and it should be W. So it'd be 1.92 times 10 to the 9th divided by 4,400 squared.
Why 4,400? You add the.
He's 400 above the surface of the Earth.
Yeah.
So the 4,000 and then 400 above the surface, right? Because the 4,000 is the distance from the center to the surface.
Okay.
What is 4,400 squared? Yeah, this we're going to need a calculator for. What's four? It's going to be 4.4 times 10 squared squared. So 4.4 squared. I mean, they did say to the nearest pound, so that's why I'm going to with the calculator. $19.36 times 10 to the 4th. So it'll be 1.936 times 10 to the 5th. All right, so let's do it this way. 1.92 10 to the 4th divided. 9,917. That can't be right. There's no way the dude weighs 9,000 pounds on a satellite. So what do we say?
Are you sure it's not 19.36 times 10 to the 6th on the bottom? 10 to the 4th would be 4.4 times 10 squared. 10 cubed.
Oh, it is 10 cubed. You're right. This is going to make more sense. That makes more sense. 99 pounds. It says weight should decrease, not increase. Just imagine landing on a planet with that much gravity that your weight goes from 120 pounds to 10,000 pounds.
Just like splat, right? Die instantly. Yeah.
Well, no, it wouldn't be an instant splat. It'd be gradual because as you get closer to the surface, the weight would start to increase. So you'd start to feel it. You wouldn't even get close to the surface before splatting down. Splat is a very good word.
How heavy of the horses do you think we could like probably get under?
Hmm?
Like, do you think like 2 times gravity? Gravity.
So what do astronauts go into training for? 4 Gs? 5 Gs?
I think so.
That's about the limit.
5.
Because even at 5 Gs, the average person would, I think even at 3 Gs, the average person would lose consciousness.
It's fast.
So 2 Gs you can manage. 3 Gs you probably lose consciousness. Astronauts have to undergo that training so they don't lose consciousness. But even 5 Gs would be really tough to live. Take your weight and multiply it by 5. I don't think it would kill you, but it'd be very, very straining on your body. Actually, so is 0 G. It doesn't strain the body, but you do atrophy. That's why they have to do strength training while they're in orbit, so that the muscles don't atrophy.
Wait, what?
They get shorter too.
What happens when there's no gravity? What's that?
They have to do they have to do training every single day, so muscles don't atrophy.
That makes sense. Because there's no forces on the muscles. So.
Yeah.
Do you get shorter? Or is that just like
You get shorter?
I don't know.
No, you're thinking of if they travel fast, and then no, even then they don't, but relatively they do. It's called length contraction. But that's relativistically speaking. They physically don't. It's just viewed that they do. They shouldn't get shorter.
That'd be great.
Ah, yes, another very common law. Volume of a given mass of gas. So this is the ideal gas law. Varies directly as temperature and inversely as the pressure. And so I think the gas law is written as Vp is equal to MNT. I believe it is. And N represents the number of moles. Right, so K would be mass times the number of moles in that case. And that's only for an ideal gas, which there is no such thing. Hey, no, they don't. They mix up their units. Why are they mixed? They use the proper units for temperature, but then the wrong units for volume and pressure. All right, so what are we told? Volume is 16 cubic inches. when the temperature is 320 Kelvin and the pressure is 300 pounds per square inch. Before I do the calculation, can anyone tell me why Kelvin is the preferred unit for temperature? And not degrees Celsius?
Does that be like the range of like, like a lot of things we measure when we use degrees Celsius.
Do they have to do like the boiling point and the freezing point? I don't know.
Yes and no. What does 0 degrees Celsius represent?
When something freezes, right?
Not something specific.
Water.
It's the freezing point of water.
Water.
What does 0 Kelvin represent?
Actually, like, I remember.
0 Kelvin is absolute zero. It's the lack of all heat. There is no negative Kelvin. That is why Kelvin is preferred.
Okay, it's more of like a true measurement. Like,
It is the true measurement of the amount of heat that there is. Whereas you can have negative Celsius. Right? 0 Celsius doesn't represent the lack of heat. It's when water freezes. Which, if I remember correctly, if I'm remembering the conversion correctly, it's 273 Kelvin is the freezing point of water. 373 Kelvin would be the boiling point of water. Conversion between Celsius and Kelvin is easy. It's just Celsius, it's degrees Celsius plus 273 to get to Kelvin. Or it'd be Kelvin minus 273 to get the degrees Celsius. Which also brings up another interesting idea. Is cold a thing?
That's what I was just gonna ask.
no,
No.
there's just the
In physics, cold isn't a thing. Heat is the thing. When we say cold, what we're really referring to is lack of heat. So that's why 0 Kelvin means
No heat.
no heat whatsoever. It's absolute zero.
Is there anything that is I will be zero.
I don't think anywhere in the universe actually hits 0 Kelvin. It gets really close to it, but there's nowhere in the universe that has 0 heat whatsoever. As far as I'm aware. Because to be 0 heat, you'd have to have no heat sources, which is definitely not true in the universe.
Anyway.
Stars are the biggest heat sources. It's true heat dissipates with distance, but again, I think that's an inverse square, so it's never actually going to dissipate to 0. It'll dissipate to very, very close to 0, but never actually reach 0. So again, I don't think there's anywhere in the universe that actually would be 0 Kelvin.
So is a black hole really hot or really cold?
A black hole is very, very hot.
Very, very hot.
Center of
Everything.
As you get closer to the center of the black hole, the heat increases exponentially.
Great.
So yes, black holes also radiate heat. Well, I'm going to be careful. They can't radiate the heat, so it's not a heat source because the heat can't escape the black hole. But once you go past the event horizon, you're going to feel it. It's going to be very hot. But it doesn't act as a heat source. No, I don't want that. So it'd be 32. I'll start with the easy one first. Might divide by 10. But 32 over 30 can be simplified. That'll be 16 over 15. Kelvin, square inches, inverse pound. Ooh, this is nice. K winds up just being 15. So it'd be 15 inch pound inverse Kelvin.
Why does that make a difference?
16 divided by 16/15ths. So we get 15T over P. Volume when temperature is 350 Kelvin. Ooh, we're getting pretty warm now. That would probably be unbearably hot for us. We figure 373 Kelvin is boiling point of water. 320 Kelvin would also be pretty warm, by the way. What did 320 be? Yeah, 320 is 116.3 degrees Fahrenheit. So that'd be also pretty unbearable. Livable, I think. Like you could probably survive a day of that kind of heat, but it wouldn't be fun. And then 350. 350 Kelvin is 170.3. That would be fatal. You would not survive for long in that kind of heat. And so 15 times 350 all over. What did you say the pressure was? 280. That's also a lot of pressure. So 15 times 35 over 28. 35 and 28 have a 7 in common. What's 15 times 5?
75.
75 quarters cubic inches would be the volume.
We never put it decimal.
Generally, we don't. Here you can because the exact form would be either 0.25, 0.5, or 0.75.
Yeah, 'cause
right? Depending on how far away it is from a multiple of 4. Which is actually a good question. 60 is divisible by 4, it'd be 60 times 15, which means 72 would be divisible by 4. So it'd be 3/4, it'd be 0.75. Something 0.75. Yeah. Question on variation.
I just this might sound like a good question, but it's variation. It's called variation.
Yeah.
I,
It's just variation.
so the variation.
There's 2 broad types of variation, direct variation and inverse variation.
Oh,
You can also think of variation as proportionality. They're the same thing.
how we call it,
And this is very important. It appears a lot in physics and the like. Even biology uses proportions. Different proportions. There's proportionalities in biology as well. So you got a few things coming up. Next week we start studying the next 2 types of functions. And by next week I mean Wednesday. Wednesday we start the exponential function. So we look at the exponential function on Wednesday. See you then.